Ooh, he's pushing the limit.
Yeah, that was easy.
Oh.
Okay. Are you Dora? That's awesome. Who's the duo?
Me. Yeah, right there.
Oh, wait, what?
Oh, I see.
Oh, Boots! I didn't see that. I can't see from here. That's awesome.
Hey, don't you look like Mama, though, off of Scooby-Doo?
A little bit, yeah. Like the hair glasses matches. But, well, that's cool. What are the other dress-up days? What's Wednesday? Family picture day. That seems like an odd one.
Yeah. I don't know what to do for that.
I heard a girl or a couple girls over here saying that they're gonna dress up as like the drunk uncles of the family, and I was like, man,
I heard someone joke about that.
that's a dicey character to play when you come to school. So I was like, okay.
That's just an
I think I think what they meant to say is like the trashy like uncle that yeah.
So is this like family stuff every time?
Yeah, when I heard that, I was thinking like awkward family photo day.
That's what it was supposed to be.
Yeah.
That was my idea.
Was it?
Yeah.
That's what I thought of when I think of like family picture
like,
day.
like
Is
those
no
ones
wonder it's a
with
bad
the
idea.
Big dad with the big glasses
Yeah.
and mustache.
or like the whole family's in turtlenecks.
Yes.
That was what I was
That's
thinking
my
of.
original.
Yeah.
That was
Dang.
the idea.
So what is it then?
It's like you dress up as a family. So like someone like the crazy uncle, the old school dad, big glasses and
The
like
mom wearing the
nerdy
sweater
stuff,
vest,
stuff like yeah,
little
Right.
tiny curly.
just like family
So
stereotypes.
wear
I
my polar
suppose.
bear sweater tomorrow.
So I want to remind you guys, the schedule this week.
Wait, you said we could take off our mask,
Oh yes, that's
Oh, yeah, 'cause
another
we're
thing.
properly
Can I have
socially
you guys sit one chair apart if you're going to take your masks off?
Oh, yes.
So again, this was something I talked about. I'm going to take this stupid thing off because I hate wearing it.
Yeah.
It's so weird.
So again, yeah, you guys separate good. As long as you guys are at least one chair apart, our class is small enough that you don't need your mask. So this will be really nice where we can, like I can actually see you guys. I don't have to talk through a muffled.
It's different.
I hear myself very differently.
Oh, yeah.
I can breathe. So this again, one, you guys are a class of mine that can handle this. Another class that they can't handle it. And two, our numbers are so small that we can actually social distance. And so that's why this is okay. Even though technically, if you're in a public space, you need it. But same thing when we went outside to do that lab. When you're outdoors and trying to stay apart, it's okay. So this will be nice. Wait until I start class before you take your masks off. Like, have everyone be seated, just so, again, we can take some safety measures. So maybe once I do attendance, I'll let you guys, like, hey, go ahead and take your masks off. I just want to be respectful of the school's policy, the state's laws, and honor that, and also not put you guys at risk. If, again, you feel uncomfortable, like, please keep your masks on, but know that we're spaced out enough. Shouldn't be an issue at all. Again, if you, like, come up to get a Kleenex or something, or we're mixing or doing a lab or something, we're going to have to put them back on. So be mindful. If you ever, like, get up to move or do something, please put your mask on before you get up. That would be great to be respectful of everybody. So homecoming, I'm just going to spend a little bit updating. So tomorrow, family picture day is the dress-up theme. Thursday is class color day. Freshmen are orange, sophomore green, junior blue, seniors pink. And then Friday is school spirit day. Thursday and Friday are the only days your schedule is changing. On Thursday, your second block of the day and ish are flipping. So you would go block 1 on Thursday is a white day. Yes. So we'd go block 1-ish, block 3, and block 2. Does that make sense? Huh? Not quite backwards. On Thursday, your second block of the day and the last block, aka ish, are flipping places. So I'm going to teach my first block. Then I'm going to teach my ish class, because they have games. Then I'm going to teach you guys, normal third block. And then I'm going to teach my second block kids at the very end of the day. That makes sense? Again, I'm most teachers should be posting this tomorrow. I'm gonna write Thursday, Friday schedule so that kids have a heads up. John?
Will that change our lunch?
No, it shouldn't because your lunch is based on your third block, correct?
Yeah.
So you guys will. I'll still have you third block, so lunches shouldn't change. I think that's why they did that because that would be a train wreck if all your lunches changed. Does that make sense? So you guys will have the same lunch, same 6th period.
So you don't have to after class, then you straight lunch.
Yeah,
I know.
and Thursday during ish, there's class competitions. They're gonna have them somewhere, the gym maybe, and then live stream them to everybody's ish. They have some interactive competitions. So like my ish class, we participate. Whoever's ish class you guys are in, you'll participate.
Whatever each class gets.
Yeah, like brain game, I think. Class competitions.
Going back.
And then in the evening, there's the Powder Puff football at 7 and the bonfire at 8:30. So that's Thursday. Friday, your schedule is exactly the same until your 4th block. Your 4th block, you do not have class. You're going to go 1st block, 2nd block, lunch, 3rd block. And then 4th block, you're going to the football field. Don't quote me. I'm pretty sure you come to your 4th block, but then you all immediately leave to the football field. So just so you're all aware, plan on coming to your 4th block on Friday. That's a red day. But just know you won't have class. You're going to show up, and then they're all going to go to the football field. At least I'm pretty sure you show up and then go. Does that make sense? But the problem is teachers are going to take attendance, and I bet you they're going to crack down if you're gone Friday without an excused absence. I would imagine they would crack down because of, unfortunately, I think you're right. Anyway, I don't want to spend any more time on that. That's ish, or homecoming schedule, stuff going on. Thursday and Friday is the only schedule changes. Everything else just dress up days and stuff. All right. So, did everyone get a chance to watch the Hooke's Law video I made? It was pretty short. It was basically me teaching Hooke's Law as if I was presenting it, but just doing it like kind of like a flipped class where you watch the material at home. Right, it's pretty short. I don't know what the final length. 16 minutes. All right, pretty short. If you're smart on YouTube, you can change the speed. You could play it at like 1.5 times speed, 2 times speed. If you wanted to save a couple minutes, as long as you can understand me. I would do that all the time with YouTube videos. I don't think you can go that high. I think 2's the limit on YouTube.
I watched my first in the last 30 seconds.
But anyway, the way I told you guys, the reason I set that up is instead of having you guys kind of struggle with the concept, which is good in a lab setting, and then connect the dots, I'm going to try it the other way, where I want to give you information, say here's what Hooke's Law is, here's how springs work, here's the equation. Then I want us, again, what we're doing right now, we're going to do a virtual lab about Hooke's Law. So again, there's another PhET simulation for springs that's really nice that I'm going to have you guys go through. Virtual students, you'll be able to access this all the same. The PhET simulation, it's actually linked on your document. Otherwise, I added the link to the classroom assignment. For you guys, look at the URL, and if it says Spring and Mass Lab, just Google PhET Spring Mass Lab, and it'll be the first one. Don't spend your time like typing https://PhET, don't type it all in. You can just Google it and it'll pop up.
You can actually even spell PhET wrong. It's still pop up.
Really? Yep. Yeah, it's well known enough. There's enough traffic to it that it really your searches kind of end up being foolproof. I do want to pass. I forgot to pass back. Brody, these were the friction labs. I basically gave you as many points as you completed the lab. If you got it all, I gave you full points. Again, I know this was hard in a sense because it was new material, but that was the point of the lab, is discovering this for your own. The lab was set up to little bit, and then connect the dots. But again, went easy and basically just gave you the points for what you completed. Yeah, Joey. Yep. If you didn't do this, if you didn't turn one in, please turn that in. Again, I warned you guys, labs are a big part of this grade, or this class. I think they're 20 or 30%. Because tests are the major part. Like, I'm required to have tests be, like, I think they're 70% of your grade. But anyway, if you didn't get this done, it's a 0, because I didn't get it from you. At least finish it and turn it in, and I can give you half credit. All right? So those were the labs from last time. This one is going to be the same thing. This lab, it's on Hooke's law, so springs. I'm going to hand these out. It's fairly short. It's 3 pages. But again, it's just step by step. Like, try this, answer a question about it. It's going to try and guide you through how springs work, how the force works. And then this shouldn't take more than like 45 minutes. So I want to try and give you half the class to finish it. I'll collect them and give you points for them. And then the second half, I want to show you some problems that we skipped from the previous notes because we weren't quite ready to like solve those problems. So that's kind of the gist of what today will be. So you'll need your computers. Again, there's 2 PhET simulations. One of them is for part 1. The other is for part 2. Now, again, look at the top of the part 1. It says, click on this hyperlink. Well, you guys can't. You can try. It's not going to work. Just look up Hooke's law PhET. That'll be the first one. Right? And then it literally goes step by step for, click the play button, choose the intro, click the 5 boxes. I mean, just follow the instructions and it'll guide you through different things that you're going to explore. Part 1 is the first 2 pages, like 2 1/3 pages. Part 2 is a different simulation. So you have to, it's a mass spring lab. So part 2, it says, hey, go to a different simulation. We'll just mass spring lab PhET. Just Google that, and that'll be the second one. And then there's just like a half a page on that second one. All right. Again, this should be more straightforward because you guys watched that, video lecture that I posted and sent you guys, where I introduced Hooke's law. I talked about the relationship, applications of it, and kind of walked through the slides so that we could spend class time just doing the lab rather than going through the notes and then having to do the lab. All right, and again, I'll be around answering questions. I'll keep my mask on so that I can come up to you guys and actually help you without breathing the Rona on you guys. Again, if you have any questions, let me know. But I want you guys to work on this. I think you guys should be able to do this in the 45 minutes. So 12:15, I'll check in and see if we're done. And then hopefully we can move on and finish a couple other practice problems that I want to go back to.
What do we measure? What's that measure? Yes, that's the Q2 on the lab question 2 says explain the slope of K, right? For the units in 2 to 3 sentences. You don't have to do 2 to 3 sentences as long as you can communicate what it is, right? What those units are, or how you know that those are the units of K.
In the opposite direction. Yep, that's all you need to play. You have to describe the size and direction of each of those. Good. I just did. Oh yeah, that's probably more complicated. Yeah, there was no, I didn't get the problem. I got one question.
Okay.
But,
Oh, so go back and do that.
yeah.
Okay. Should be for history.
Alright.
Already did that.
Yeah.
Okay. Andre, you doing good? You have a question?
No.
Okay. Are you doing all right?
How are we gonna get this choice? What you need is, we can put the units as just units divided by units. Calculate, like, you choose 3 units, here is units by units. Then question 3 should help clarify that or remove significance of it. You can adjust it and see how the spring responds. Make sure you do it right. In this situation, I call 30 minutes.
Oh, this is this.
Yeah, that's like if I do 7, 0, that's no force, no displacement. That's my natural state. The spring would just be that long if it was 7, 0. My force is displaced. Spring is displaced from its natural point.
About 7 meters.
Correct. You write that. And make up another applied force.
Okay.
Right? So you could try like good idea to say double that. Right? Go 60. Yeah. So record that. Yeah, that's good observation. Try a couple other ones. Now you would try like a negative 30 force. Because I negative, I said because it's a negative expression. What's your displacement? Expression.
Negative.
Negative. That's another observation. Point. Yeah. So you should, that should help you kind of build this relationship between 5 force, this much in this direction.
And that's why her room put negative 0.5, and it doesn't say negative 0.5, it says 0.5 and negative.
But the displacement is a vector, magnitude and direction. You just give me a number.
It'll be-
Yeah, because I don't know which way it is placed.
I just noticed it didn't show it right here, but because it has the arrow that's indicating negative.
Correct.
Okay.
That's exactly right. That's why you're going to put negative 30. This is a negative. I realize it doesn't. I'm applying it to the left.
Mm-hmm.
It's not a negative 30, but I know it's negative because that's what I define as a negative. And it's important because it has a lot of impact on the relationship.
Mm-hmm.
Yeah. But those are great data points to kind of draw out that connection. again, that's an example. I personally recommend always write the equation. You always start with using equations that define physically, and then plug in.
Understood this, that's fine.
Yeah. You're right here. The force is negative kx. Yeah. And you applied it in the positive direction, so that's good. Make sure your negative's there. Negative kx. And do this divided by that. Right, simple algebra. You want to get rid of divide both sides. It basically should be the inverse of that. Right? I take this divided by. I do want to divide by. You just did the math backwards, that's all.
Yep.
I don't think you need it exactly. You're right. You can get a general. Yeah. What? That's your prediction. But then you'll actually do it. Oh, yeah, my idea is right. Calculating exactly. Yeah. So you do not need like a numerical prediction. You can give a description of exactly what you said will happen. That's perfect. What's up?
My computer's at 1%. Oh, I just gave him the, I don't know what, like, percent his computer. It's open.
Oh, it's at 48. It'll be fine.
Yeah, just steal it back from them.
There it is.
Hopefully you guys are getting close-ish. I want to give you like 10, 15 more minutes. Hopefully you guys are near the end. I think most of you were almost to that last section.
spring in series. Phenomenon is an actual word to describe why that is. A phenomenon is just something you observe in nature. Yeah, but does that make sense? I think it's a phenomenon. Phenomenon is something. Like, is it an exact name for why it is? No. When it says explain the phenomena, it's just like explain what it is. Yeah, explain the phenomena of springs in series and what happens with them. Yeah, so phenomena is what you observed when you put two springs in series. It's actually like explain like why is that happening or what's going on across it. Okay, this one, all you're going to do is use, remember, spring force? This equation says the force of the spring equals negative kx. K is the spring constant, x is the displacement. I think what happens if you apply 75 newtons to a spring that has a spring constant of 400. Basically, use this equation, plug in what you know, and solve for the displacement and the deformation. So all you'll really do is plug in shove it, solve for x. That's what Oh, that one, you would read this and see like, hey, this is our equation for spring force. Predict the deformation or displacement of a spring if it has a spring constant like K, 400, and a spring 75 newtons. So basically use this equation. Yeah. And then x is solving for that deformation or displacement. So then you know your equation, you plug it in, just do it on solve for x. Yep. Yeah. That's your prediction based on this equation that you said it's supposed to work. Like basically. Yes, because you're solving for x. X is the displacement from rest. Yeah. Yep.
If you guys are on that part 2, the very last one, you only need like 2 at minimum or 3 data points, right? It's asking you to plot graph mass versus force. Even 2 data points will technically give you the answer. 3 would be good, but you don't have to go through and get 10 data points for part 2 of the lab. Just to save you guys some time. you guys another 5 minutes to finish up, and then we'll turn these in, and we gotta do a couple other small things before we leave today.
Like recognition and putting it in the way we write it, and having to use caret symbols. That's super big. Yeah, that's a good one.
Sean, question?
Yeah, like the weight on it and measuring the y-axis you want force spring, and x-axis you want basically just put x, right? The displacement. So when you put like say 50 grams, you see how much it displaced? Use natural language. Click all these check boxes. Up. Did you see that? Oh, that you can help you kind of see where you're at. So you know from the start, it starts, natural length is what? 48. You got 48, and it stretches all the way down to what? 56. Yeah, so the difference is your elongation. So 8. So you can put like 8. 8. Oh, but that's in centimeters. That's millimeters. You can do millimeters if you want. Right? So if I have 8 millimeters, what was the force? 50? Right? Because I put, oh no, it's not. I need newtons. I convert 50 grams to newtons. How many kilograms is that? 05. And then force of gravity equals 10 g. You can do times 10. This is actually 0.5 newtons. That's a data point. Then you do one more. Take that off or put a 100 degree on it or something. Yeah, it's enough. So when you do 100, 48 to 16? Yeah, 16, right? So now you're at 16. What was the mass? Well, 1 kilograms. here, what's that rise? 0.5. And how far did I go over? 8 millimeters. So that's, what is that, 16? Right? Should be. Divided by 8. Oh, wait. No, that's right. We'll plug both by 2. This goes to 1. Yeah, that's your slope. What's the significance of that slope? Yep. Spring. Yes. Wait, not spring papers. Oh, no, that's constant. Yeah, also spring constant is bigger. That's what that slope is. So the ratio of the force divided by the displacement tells you the stiffness of the string. Yeah, good.
All right, so you guys, I need to. I'm gonna bring you back. One thing I want to do quickly is show you. I'm gonna collect these before you leave. If you're not quite done, that's okay. But I need you to pay attention to me for a little bit before we end the day. I want to get through and at least touch base on these 2 topics that were from our old notes, but I skipped because we weren't quite ready for them. So, one example. Oh, hold on. One example is problems where we need to solve the force of like tension in 2 strings. If we solve tension of a mass hanging from a ceiling, well, gravity acts on the mass, and the string provides tension to keep it stable. Well, what happens if you have 2 strings? What happens if you have one mass hung by 2 different strings? How do I figure out how much tension is in that rope? If it's vertical, that's easy. The tension is equal to the force of gravity on that object. Well, crap. How do I do it if I got 2 strings pulling in 2 directions? Well, what you want to go back to is look at your x and y directions, right? So if I have this string and this string, you remember how we resolved force vectors? We broke the force into x and y components, and then we summed all the x's, summed all the y's. That's what you do here. This is the force of tension. Well, I don't want it in this direction. I want to break it into an x component and a y component. This is where you go back to your trig, right? These strings are pulling in this direction. Well, some part of it is pulling this way. Another part is pulling up, right? In the x direction, this object's not moving. There's no acceleration. So these x components need to be equal. Some of the forces in x should add up to 0. Some of the forces in y should add up to 0. Do you see how in the y direction, they don't really do the math in this one. This string pulls up 5 newtons. This string pulls up 5 newtons. Do you see how 5 newtons up balances 10 newtons down?
Once you know that, then you can do your math and figure out what's the actual force in the tension direction, right? They're skipping a bunch of trig to figure it out. This gets crazy. This is pointing out like, hey, if I have an object that's hanging and I put two strings kind of close to each other, these arrows show the magnitude of tension. What happens if I make them wider apart? Wider apart. Wider apart. Do you see how the magnitude of the tension gets much bigger? Right? The wider my angle is holding this one mass, the wider the angle, the greater the tension is. Do you know why that is? If your string is this far out, like strung at this angle compared to straight up and down, which string can more easily provide an upward force? Isn't it the string hanging straight down? All the tension in the string can apply directly to balance out the weight. Well, if I have it strung at an angle, only the y component can balance the weight. Well, that's it's an increasingly smaller part of the angle. Did you know that it's physically impossible? Oh, I don't have a demo ready. Dang it. Yes, yikes. My brain got ahead of my preparation. I need a string or a rope. Here's a literal rope. Right? I'm also going to need a big mass. Yeah. Here we go. Pulling stuff out of my butt. All right. Right? If I'm holding this string or this big mass, yeah. So if I hold it like this, this is easy for me to hold. I'm not working hard to do this. It's a little harder.
It's a bit of a shoulder muscle.
Yeah. Yes.
There's the broken sword.
Oh, I can't run it through the middle. I need it to stay balanced. So if I try to... That is my best effort. I'm not faking this.
Let's get it, Brody.
Yeah, can we do it?
Brody, you want to try this? So what I'm doing is I'm trying to move the angle of that tension as far out as I can. I'm gonna bust that tile.
Do it.
Okay, so Brody, I'm gonna have you face forward. So you're gonna put this weight on, and you're gonna pull outward, change the angle, and see how close to parallel you. That's pretty good.
Wow, Brody.
That's good. Okay. Did you see that? So Brody, I think, did a little better than I did.
No, Brody.
But was he parallel?
Well,
Would you be mad at me if I told you it's impossible to do that?
That's a lot harder than I thought.
It is, right? I wasn't faking it. It's literally, you have to apply an enormous force. The reason is, thank you, Brody.
Wait, what if you two did like tug of war and you have that in the middle?
Do you know why that it's impossible to hold any sort of weight parallel on a string? Because if you hold that rope parallel, what force can pull up? All of the tension is in the x direction. That means you can't apply any force in the y direction to counteract the mass. That's why it's impossible. Even if you had a paper clip on a fishing string, paper clip doesn't have a lot of mass. you still can never pull it hard enough until that string is parallel. It'll always be some sort of angle because you need some sort of force that pulls up to counteract the weight. Now, when you solve these problems, you're going to do trig.
Now, what if there's a smaller rope? Like, what if you put a paper clip on that rope?
You couldn't do it, but the problem is it's too thick. You couldn't actually see the angle. That you would have like a third of a degree angle. Like you visually couldn't see the angle that rope is creating. But I want to quickly show you, if you're to solve a problem, right? You got a rope at a 30-degree angle. What is this tension? Well, you see, 100 pounds, same angle. So they each give half of the supporting force. So you know this force in the y direction, each of them is 50 pounds. This is 50 pounds, and then I have some x. The other side, also 50 pounds, some x. Just do trig, right? You know the angles. They give you the shortcut. The sine of 30 degrees, right? This angle here, which is the same as this angle. Sine of 30 is opposite over hypotenuse. Sine of 30 is opposite, which we know, over hypotenuse, which you don't do your trig and calculate. The tension in that rope, oh, it doesn't give it. I don't actually know the answer. I can't do that math in my head. But my point is, if you have a tension problem, you need to break it into x and y components, and oftentimes you'll have to just do your trig, right? That's why your SOHCAHTOA, sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, tangent is opposite over adjacent. You'll need to know that if you're going to resolve like tension forces or multiple hanging objects. The last thing, and again we'll practice this next time, is friction on a sloped surface. This is a common problem where they have a block on a plane, right? They're asking you, hey, is this block going to slide? Will it slide down the ramp or will it stay there? The challenge is, it said your parallel force, right? Oh, they did the math already. They told you that this block weighs 75 pounds. So I need to break it into what force of gravity is pulling along the inclined surface, what's pushing normal. So I just do my math. This is a 27-degree slope. This angle is 27 degrees. I know this, I say, sine of 27 is opposite over hypotenuse. Solve for the force pulling down the ramp. Then I do cosine of 27 is adjacent over hypotenuse. Solve for what force of the weight is pushing into the plane. Well, now I have my normal force, don't I? Normal force is what acts perpendicular to the surface. It's what supports it. Well, can I figure out friction if I know that? What's the equation for static friction? Remember this? Friction equals the coefficient of friction times normal force. When we have static, it's anything up to that limit. What happens after you exceed the static friction limit? Yes, it dips. The force of friction dips, and you're now in kinetic friction. The question is it going to slide? All you really want to know is the force of the block pushing down the ramp greater than the friction force trying to keep it still. Well, I know that all this, I know 0.4, my normal force is 67. 27 pounds is my static friction limit. And I'm at 34. Not quite. The component of the weight pushing down the ramp is larger than my static friction force resisting it. So what happens? It's sliding. Do you see this force imbalance? Newton's second law. F equals ma. I add up positive 27, negative 34. I get negative, what, 7? Well, if I have a net force, don't I cause acceleration? It's going to start accelerating down the ramp. So the same way, you will see a lot of inclined plane problems. You'll throw an object on an inclined plane and say, somebody's pushing with 10 newtons up the plane, and the friction coefficient is blank. Is the object moving or not? Well, all you do is find all the forces, sum them all up, and say, the force is acting in this direction. Is there a net force? Or are they balanced? If there's a net force, is it pushing up the ramp or down the ramp? Well, wherever it's pushing, that's causing motion. If those forces are balanced, equal and opposite, F equals ma says, 0 equals mass times acceleration. I can't have 0 mass, therefore my acceleration is 0. So that was a free body diagram of what we just did. And there's other examples they can give you. Does it make sense? I only wanted to show you the process of tension problems. If you have 2 tensions, you need to resolve both of them. Sometimes they're going to be at different angles. Then you need to solve each one independently based on whatever angle it's at. And then when you have an inclined plane, you should always know gravity points straight down. Always straight down to the center of the earth. That's what's being applied. What you want to do is you resolve gravity into x and y components. Now you don't want x and y. It's already like that. You want to know force in the plane direction and force in the perpendicular plane direction. Well, just draw a triangle. Use your angles that they give you and use trig to solve for the components. Then you know the force of the block pushing into the plane is supported by that normal force because it's not moving in or out of the plane or the ramp. Well, then you got this force pulling down the ramp. Well, what opposes that? There's friction. Friction opposes the motion. I can calculate that. Then I do F equals ma. And then I can tell, hey, this isn't moving. I'm pretty sure this one doesn't move because it's got a much higher coefficient of friction. You see that? Same scenario as we just did, much higher friction coefficient. These two surfaces are very grippy. The friction is very strong. So the weight of this block isn't enough to overcome static friction. So static friction will just equal whatever it's given. This is not true. This would mean that friction is launching the block up the ramp.
Yes.
This is a misnomer. Friction equals and resists what it is pushed on, basically. The block is trying to slide down the ramp. Static friction opposes it. It can oppose it exactly up to this limit. I don't know if they fix it. Yeah, that's baloney, right? Physics does not work that way. You can't put a block on a ramp and friction moves it up the ramp, right? That's baloney. If that's the case, that's how I'm going to launch my space shuttle into orbit.
Oh, yeah.
I'm going to just tip it on its side on a ramp and let friction launch it into space.
Make it
No,
make
fix
it
it.
real light.
Physics doesn't work that way.
Can you imagine? Because then
It's
if a
absurd.
Kid, then if a kid tried to go like on the slide, you just go.
Yeah,
Gets on a
it
slide.
tries to climb up it. This is the limit.
This is the absolute maximum. Anything less, it's going to just equal what it's applied. So the actual static friction force is what it needs to oppose to stay steady. As soon as you exceed that maximum, you now switch to kinetic. All right, I think that's all I wanted. We'll try and, man, I really hope I didn't bust that tile. I'm actually surprised that I didn't.
You should have seen what they were doing in the other class. It was one of the other classrooms that they were banging.
Yeah?
They had like a big rock and they were taking a hammer and they were smashing.
Oh, jeez.
And like it would spark and they'd outdrive on it.
Oh my gosh.
So I think you're fine.
Okay. Couple things I want to point out, you guys. One, these labs I need you to turn in before you leave, right? Hopefully you guys I've given you enough extra time that you finished it. Make sure you get those to me before you leave, and I'll throw those in the grade book. Basically, again, if you did them, I'm going to give you points. Virtual students, same thing. You'll have to submit it, I think, by tomorrow night. You can either print it out and do the lab and then take pictures and put in the classroom, or you can download the Word doc and just type in your answers if you want to. But again, that needs to be submitted by tomorrow night. I sent you all an email. Maggie asked me about it just now. There's like a Indiana AP Teacher Association or something that I actually wasn't aware of. They offer study sessions, like I think across the state. It's like a virtual Zoom study session. That email is the first one they have. It's kinematic, so it's a review of Unit 1. But if you want to be reviewing and staying on top of material as you go, that would be a good thing. You can just hop on that meeting, and it's just a Zoom study session. There's 4 different time slots. It's the same study session. Don't go to multiple. You'll see the exact same thing. But if one of them works for your schedule and you want to attend, by all means, I wanted to make that opportunity available to you. It's not, I don't know the teachers, but it's other AP teachers in this organization across the state of Indiana. And again, that first study session, the topic basically was motion graphs, velocity, acceleration, essentially a review of what we did last unit in kinematics. So I at least wanted to make that available if you guys are all interested in an extra study session to review. That's available. I sent you the link, and you can join that Zoom link meeting. I think that's it. Again, make sure you put your mask on before you leave, please. I'll collect these labs on your way out. And then we will see you guys Thursday. Class will be normal. I'll try to lighten it up for you guys. I know it's homecoming. We still got to get stuff done, but I'll plan a buffer in our class for free time.
How about we all just play Among Us?
Yeah. Thank you.
I like the idea.
Thank you. Good to see you guys. Nice outfits. I totally understand now that I see the boots. I couldn't see it from up front, but I'm awesome. That's nice. Yep, thank you. Good. They played some good classics. Andre Ayton on yours?
Yeah.
Good deal. Brody, did I get yours?
I gotta find it. I think I put it in here, I think, somewhere.
I was gonna say you just have it.
Check out the
Okay, I got those. Good. Aiden, did you want to try this?
Sure.
So just don't like jerk it around. So basically you just grab, a certain like foot away or something. And just pull it apart. You see that?
Yeah.
I can still see the angle. The point is you literally need infinite force if you're gonna pull it strong enough that it can be completely level. That was my point in demonstrating that. Because again, I wasn't just
making a show and pretending like it's difficult. It's literally like the amount of strength to pull it this way. I mean, I should have had you guys try it in a lab and just not told you that it's impossible. You guys might have hated me for it, but it's a good demo because it's a simple thing, but much more complex than you think.
Those are the only books I really have. Somewhat.
He's never seen any movie, okay?
Dude, I had an amazing
It's okay.
I had an amazing idea. So today, I woke up this morning. I wanted to get me and a friend to do white chips. The two white chips people. But it was too late for that.
Do the secret
But it was too late for that when I woke up. Is gonna come with
Kevin and Marcus. That movie is my favorite movie of all time. This is probably the only thing I have actually on DVD.
Whoops.